Hello everyone. So finally it's time for me to do the extended response for 2023 Physics VCAA exam. I'm so sorry I couldn't upload it yesterday because I had some commitments. But anyway, so let us get started. So some physics students are conducting an experiment investigating both electrostatic and gravitational forces. They suspend two equally charged balls, each mass of 4 grams, from light, non-conducting strings suspended from a low ceiling. Okay. The charged ball repel each other with the strings at an angle of 60 degrees as shown in figure 1. Cool. There are three forces acting on each ball: tension, gravitational, and electrostatic. On figure 1, use the labels T, F, G, F, E. Draw each of the three forces acting on each of the charged balls. Okay, so there's be tension, which is just in the string. So here, this is our tension for both. Then there will be gravity. So here Fg, and here Fg, and then there will be the force Fe because they are repelling, Fe. Okay, so that is done. Moving on, so that the tension force T in each string is 4.5 times 10 to the power of -2 Newton. Use 9.8 Newton. Okay, use G as, okay, 9.8, cool. Now what we can do is we can construct a triangle like so, where this is our tension, this is our Fe, and this is our Fg. So basically what I've done is I've just bisected this thing into two, so meaning that this angle will be 30. And now we can just use this triangle over here to calculate our stuff that we are asked to calculate. So we are asked to calculate the tension, more like show, but yeah. So we know our F, we know our gravitational force. We are given the mass, so we can easily calculate that. So we can say cosine of 30 is going to equals to Fg divided by tension, meaning that tension is going to be Fg over cosine of 30. Now what was the mass of the ball? So 4 grams. So because they said tension in each string, so we'll just take 4 grams, so which is going to be 4 times 10 to the power of -3 kilograms times 9.8 divided by cosine of 30. So let me calculate this, and hopefully this should give us what they want. So 4 times 10 to the power of -3. Cosine of 30. Yep, so that gives us exactly what they are looking for, which is going to be 4.52. But since they want just 4.5, I'm going to leave that as 4.5 times 10 to the -2 newtons. Calculate the magnitude of electrostatic force, Fe. Show your working. So we can again use the same triangle like we did over here and use that, but instead of using cosine theta, we can use tangent theta. So tangent of 30 is equals to Fe on Fg. Now the only reason why I'm not using tension is because, well, if they didn't give us this number, then I might have very well calculated tension wrong, and that mistake would have been carried over. So that's why I'm using the values that is given. So that's one tip I can give you. So Fe is equals to Fg times tangent of 30, which will be 0.4 times 10 to the -3 times 9.8 times tangent of 30. Oh no, not 0.4, 4. Okay, there we go. Alright, so let me punch that in the calculator. I was just making sure that I didn't write 0.4 for the question above this. So 4 times 10 to the -3 times 9.8 times tangent 30. So we will get 2.26 times 10 to the -2 Newton. So that will be our answer for this. Moving on, Phobos is a small moon in a circular orbit around Mars at an altitude of 6,000 kilometers above the surface of Mars. Okay. The gravitational field strength of Mars at its surface is this. The radius of Mars is that. Show that the gravitational field strength 6,000 kilometers above is going to be that. Okay, so we know that G equals to Gm on R squared. Now this over here is going to be constant. So we can say that G is inversely proportional to R squared. And now we can just simply use this proportionality to find the answer. So it will be 1 on 6,000 plus 3390 over 3390. So we are just basically like getting the ratio kind of a deal by using this. And if I were to punch that in my calculator, 1 on 90 over 3390 to the power of 2, and we will get 0.130 roughly. Now we can say that G at 6,000 kilometers would be 3.72, which is here, times 0.13 times that. So we get 0.48 Newton per kilogram as required. Calculate the orbital period of Phobos. Give your answer in second. I apologize if I did pronounce it incorrectly, but anyway. So force centripetal equals to gravitational force for this. So we'll get 4 pi squared Rm over T squared equals to mg. So m and m cancels out. So T squared equals to 4 pi squared R on G, implying that T is going to equals to 4 pi squared R on G, square root of that basically. So now we can substitute in the numbers. So 4 pi squared times the radius, which is going to be 6,000 plus 3390 times 10 to the power of 3 conversion over 0.48. Okay, so let me just punch that in my calculator. So I get 2.779 times 10 to the power of 4, but I'll just maybe write it as 2.78 times 10 to the power of 4 seconds. 10 to the power of 4. Okay, Phobos is very slowly getting closer to Mars as it orbits. Will the orbital period of Phobos become shorter, stay the same, or become longer as it orbits closer to the Mars? Explain your reasoning. So it is going to become shorter. The reason being that R cubed on T squared equals to Gm on 4 pi squared. Now all of this is going to be constant, meaning that R cubed is proportional to T squared, and hence we can say that as radius decreases, the period also decreases, and hence period of Phobos will become shorter. Okay, moving on. Two long straight current carrying wires P and Q are parallel as shown in figure 2a. The current in the wires is the same in magnitude and opposite in direction. Okay, so on figure 2b, sketch the magnetic field around the wire showing the direction of the magnetic field. Use at least 5 lines. Right. So if I were to use my right hand, my thumb pointing into the page and fingers curl, so our magnetic field for this will be like so. Okay, they're a bit off center, but yeah, so I'm gonna draw maybe 6 lines for each. Okay, that was a bad idea, but maybe I can just like maybe I can do like that. Yeah, okay, I'll probably lose a mark here, but you guys get the point. So now if I were to point my finger out of the page and curl, it's going to go this way. So like that, like this, and another line if I can fit. No, I cannot. Okay, maybe I can just barely fit in, but yeah, don't draw like me, please. That will just lose it. That will just lose you some marks. But so this is just like the basic idea. If you drew something like this, like a bit more better, you'll get full marks. So all good. Do the two wires P and Q attract or repel each other? Now they have current flowing in opposite directions, so they will repel. And for explanation, we can using the right hand slab rule. It can be determined that P and Q repel each other, meaning actually maybe a new sentence saying that applying Newton's third law, which states that F on Q by P is equals to negative of F on P by Q. Now to show you like a bit of a visual, I can maybe like draw a diagram here. I can't show you my hand, but I can draw you a diagram. So our current is going out of the page here, right? So this is our current out of the page, So magnetic field is going this way. Now if I were to use my right hand slab rule to match these two, we will get our force going this way. And this is for P. For Q, current is going into the page, so I into page, right? And our B is going this way, a magnetic field. So that means our force is going to go this way if you apply the right hand slab rule. Okay? Moving on, a transformer question. Okay, so a transformer is used to provide a low voltage supply for 6 outdoor garden globes. The circuit is shown in figure 3. Assume there is no power loss in connecting wires. All the voltage values are RMS values. Okay. The input of the transformer is connected to a power supply that provides an AC voltage of 240 volt. The globes in the circuit are designed to operate with an AC voltage of 12 volts. Each globe is designed to operate with a power of 20 watt. Okay. Assuming that the transformer is ideal, calculate the ratio of primary turns to secondary turns of the transformer. So it's going to be 240 ratio 12, which is going to equals to 20 ratio 1. So our answer is going to be 20 ratio 1. The globes are turned on, so all of them, I guess. So how many others? There are 6 of them. Okay. Calculate the current in the primary coil of the transformer. So total power is going to be equals to 20 times 6 because there are 6 light globes and each of them uses 20 watt. So we'll get 120 watt. Now we know that power equals to VI, which implies that I equals to P on V, and hence 120 on 240, I think that was? Yep, 240, which will means that we get 0.5 amperes. Okay. Explain why the input to the current to the explain why the input current to the primary coil of the transformer must be AC rather than constant DC for the globes to shine. Right, okay, so since constant current produces a constant magnetic field, there is, oh wait, not constant magnetic, yeah, no, there is no change in magnetic flux. Sorry, I got my words the other way around in my head. Okay, which implies that no EMF is generated. Hence, no bulbs will shine. Therefore, the input current to the primary coil must be AC. Okay, I'm just going to read it one more time just to make sure it makes sense. Since the constant current produces a constant magnetic field, there is no change in flux, which implies that there is no EMF. Okay, hence no bulbs shine. Therefore, the input current to the primary coil must be AC. There we go. Alright. Question number 5. Figure 4a shows a single square loop of conducting wire placed just outside a constant uniform magnetic field B. The length of each side of the loop is 0. Okay. The magnetic field has a magnitude of 0.3 and is directed out of the page. Right. Over a time period of 0.5 seconds, the loop is moved at a constant speed from completely outside the magnetic field to completely inside the magnetic field. Okay. Calculate the average EMF produced in the loop as it moves from the position just outside the region of the field to the position completely inside the magnetic field. Show you're working. Right, so EMF average is going to be equals to negative N, which is the number of coils, times change in magnetic flux over change in time. So the coil, they didn't mention anything, so I'm just going to say that it has only one coil, times, there we go, 0.04 squared, because change in magnetic flux is B times A, times 0.3 times divided by 0.5. So let me just punch that in my calculator. Okay, so I get negative 9.6 times 10 to the power of 4, or negative 4 voltage. So negative 9.6 times 10 to the power of negative 4. Okay, moving on. On a small square loop in figure 5, show the direction of the induced current as loop moves in the area of magnetic field. So it is going to be this, like that. Okay, moving on. Kim and Charlie are attempting to create a DC generator and have arranged the magnets along the axis of rotation while loop JKLM. Okay, as shown in figure 6, they are having some trouble getting it to work. Yep, obviously. They rotate the loop in the direction of the arrow shown in figure 6. Using physics concept, explain why this orientation of the magnets will not generate an EMF. Well, since the magnets are parallel to the coil, no magnetic flux is generated, and hence no EMF is induced. So Kim and Charlie decide to move the magnets so that EMF is generated. On figure 6, draw the position of the magnets to ensure that EMF is generated. Okay, so this can be our north, and this will be south. So now it will be generated. Cool. So done on the diagram. The two high voltage transmission lines span a distance of 260 km between power plant A and town B. As shown in figure 7, power plant A provides 350 power. The potential difference at power plant is that. The current in the transmission line has an RMS value of that, and the power loss in the transmission line is this. Okay. Show using calculations that the total resistance of two transmission line is 41 ohms. So we know that power loss is equals to I squared R. So R is equals to power loss on I squared. So power loss is going to be 20 times 10 to the power of 6 conversion, because this is megawatts, I think, and we're converting into just watts, divide by I squared, which is what 700 amps. 700 squared, so that should give me about 41 ohms. So 20 times 10 to the power of 6 on 700 squared. Yep, so it is giving me 40.8 ohms, 40.8, sorry, not 1, 40.8 ohms. Now that is equivalent, or rounding it up, to 41 ohms. Moving on, town needs a minimum of 480 kilovoltage. Determine whether 480 will be available to town B. Show your working. Right, so for this, we need to find out how much of the total power that is reaching the town B. So there is 20 megawatt just lost out of 350 megawatts. So we can say that power reaching the town is going to equals to 350 minus 20, which is going to be 330 megawatts. So P equals to VI. Now we're just substituting in the values to find the voltage that is supplied, because we know the resistance, we know the current as well. So V equals to P on I, so power is going to be 330 times 10 to the power of 6, converting again, divide by 700, which is the current, and that will give us 330 times 10 to the power of 6 over 700, 4.714. Okay, maybe I'll just leave the 4 out, times 10 to the power of 5 volts, because we converted that, so it has to be in the standard unit. And 480 kilowatts voltage is going to be 4.8 times 10 to the power of 5 volt. And since 4.71 times 10 to the power of 5 is less than 4.8 times 10 to the power of 5, town B will not have 4.8 times 10 to the 5 volts. Explain what would happen if electricity between power plant A and town B were to be transmitted at 50 kilovoltage instead of 500. Assume that the resistance of the transmission line assume that the resistance is still 41. Okay, so P equals to VI, and I is going to be, well, power is going to be constant, so I is going to be inversely proportional to the voltage. And from this we can say, since voltage decreases, current increases. And now we can use power loss formula. So power loss is equals to I squared R. So that implies that P loss is proportional to I squared. So this shows that there will be 100 times more power loss. Power loss. Wow, okay. So, okay, at a skate park, and she stands on her skateboard as it rolls in a straight line down a gentle slope at a constant speed of 3 meters per second. The slope is 5 degrees to the horizontal. The combined mass of that, and okay, so 65. In figure 9, the combined system of the, I'm just going to say Maya, and skateboard is modeled as a small box with point M at the center of mass. Draw and label the arrows to represent each forces acting on the system that is that skateboard as they roll down the slope. So there will be our gravity, Fg, then there will be normal force, Fn, and have they mentioned anything about the friction? No, they haven't said friction, like it's friction free or anything, so I'm just gonna say there is friction, and I'm gonna add it over here, F of friction. So I'm just gonna make a label too, gravitational force, just so that gravitational force, forgot how to spell that. Fn is the normal force, and F is the friction. Calculate the magnitude of total frictional forces, okay, acting on, okay, so that is just going to be F is going to be mg sine of theta, which is going to be 65, because that's the total mass, right? Yeah, 65 times 9.8 times sine of 5, because 5 degrees. And let me see what it gives me. So 65 times 9.8 times sine of 5. So I get 55.5. So 55.5 Newton. So 55.5 Newton. Near the bottom of the ramp, Maya takes hold of a large pole and comes to the complete rest while still standing on the skateboard. Maya and the skateboard now have no momentum or kinetic energy. Explain what happened to both momentum and kinetic energy. No calculations are required. Okay, so all the kinetic energy was lost in the form of heat. That's always one factor. And what could be the other one? So if I were to bump in a pole, or maybe just even hold, yeah, that would make a sound. Heat, or heat and sound energy. all the momentum was transferred to the large pole, Okay. Georgos. Okay, I'm sorry if I pronounce it wrong. I'm just gonna call G. G is practicing his tennis serve using a tennis ball of mass 56 grams. Right. G practices throwing the ball vertically upwards from point A to point B as shown in figure 10. Okay. His daughter Eka, a physics student, models the throw assuming that the ball is at the level of G's shoulder at point A. Okay. Both when it leaves his hand and also when he catches it again. Okay, so point A is 1.8 meter from the ground. The ball reaches a maximum height of point B, which is 1.8 meters above G's shoulder. Show that ball is in the air for 1.2 seconds from the time it leaves G's hand, which is level with his shoulder until he catches it again at the same height. Right. So we have to use this formula. The delta y equals to uyt plus half at squared. Now there's no initial vertical velocity, so we can say uy is equals to 0 meters per second. Therefore, it is going to be half at squared, and we can say that t squared is therefore going to be 2 delta y on a. So t is going to be 2 delta y on a, square root of that. And now what do we do about delta y? It cannot be like, because delta y cannot be 0, so I can't take into account like the whole journey in one go. I have to do half and half. So I have to calculate the time for, I have to basically calculate the time it took to reach at the maximum height, and then times it by 2 is going to be how it's done. So t equals to 2 times 1.8, so this height over here, 1.8, on acceleration, which is 9.8. Okay, so that will give us t equals to, let me just punch that in my calculator again, times 1.8 on 9.8. Right, so that is going to give us 0.606 seconds. Now we multiply that by 2, 0.606 times 2, and we will get 1.2 seconds roughly, 1.21 seconds. Okay. G swings his racket from point D through point C, okay, which is horizontally behind him at shoulder height, okay, as shown in figure 11, yep, to point B, okay, so like that. Eka models this swing as a circular motion of the racket head. The center of the racket moves with constant speed in a circular arc of radius 1.8 from point C to point B. So the radius is 1.8. Right. The racket passes point C at the same time that the ball is released at point A, and then the racket hits the ball at point B. Calculate the speed of the racket at point C. So speed equals to distance on time, which will be, what is our distance? So 2 pi r divided by 4. So 2 pi times 1.8 divided by 4. And then the time is... what is the time? Oh wait, it's right here. It's okay. Wow, okay, so it's going to be 0.606 that we just found. Wow, okay. Okay. So just putting that in my calculator. 2 pi times 1.814 and 0.606. So I will get 4.67 times 10 to the, no, not 10 to the power of 0. Cool. So 4.67 meters a second. Interesting. Wait, so they said that we have to show that ball is in the air for 1.2 seconds. So do we just assume that it's 0.6 and not 0.606? And first of all, I need to fix this. So 1.1 second, which is almost equal to 1.2 seconds. So do I assume that t is going to be 0.6, or do I take in the actual value? Well, they say that it's going to be 1.2. Maybe I'll just take 0.6 and not the actual value, I guess. So 0.6. So okay, never mind. So 4.71 meters per second. I don't know which one is right, but I think we have to go with 0.6 because they said that it's going to be like 0.2, so I just divided by 2. Yeah, if it's wrong, just let me know down in the comments and I'll be clarifying it. Thank you. So the ball leaves G's racket with an initial speed of 24 meters per second in a horizontal direction. As shown, a tennis net is loaded 12 meters in front of G and has a height of 0.9 meters. How far above the net will the ball be when it passes above the net? Assume that there is no air resistance. Show your working. Okay, so first we have to find out the time taken for this ball to finish this journey. So delta x, which is going to be the change in the x direction, is going to be initial velocity times t. So t is going to be that on that. So that is going to be 12. Yep. On what was the initial one? 24. Okay, good. 24, which is going to be 0.5 seconds. So delta y is going to be uyt plus half ayt squared. So we know that there is no initial vertical velocity, so uy is just going to be 0 meters per second. So therefore, delta y is equals to 1 on 2 times negative 9.8 times t squared, which is 0.5 whole squared. So we will get a change of, let me just calculate, so 0.5 times negative 9.8 times 0.5 squared. So we will get negative 1.225 meters. Okay, so it was at the height of 3.6, and then it went down by this much amount, so negative 1.225. So I wonder what would be the value over here. So 3.6 minus 1.225. So the value here is 2.375 meters, and now we just have to like subtract 2.375 and 90 to get this distance over here. Maybe I should call it h or something, but yeah. So our final answer would be, okay, so first I need to show my step, that 3.6 minus 1.225, which is going to be equals to 2.375 meters. That is our height from the ground of the ball after it travels for 0.5 seconds, and it's when it's just above the net. So now we know that we can just do 2.375 minus 0.90, and we'll get 1.475 meters. So this distance over here is going to be 1.475 meters. So this is where the ball is going to be right over here. So distance between these 2 points is going to be 1.475. So our answer is going to be 1.475 meters. Moving on, a proton in an accelerator beamline of proper length 4.8 kilometer has a Lorentz factor of 2. Calculate the speed of proton relative to the beamline in terms of c, so speed of light, in a vacuum. Give your answer through to 3 significant figures. So V equals to c times 1 minus 1 on Lorentz factor squared. So that would mean that, wait, I don't need a vertical line. So that would just mean that c times 1 minus 1 on 2 squared, so 4, which is going to be, I'm just going to calculate this third over here and then times it by c, so 1 minus 1 on 4. So I get 0.866c. So 0.866c is going to be our answer. Calculate the length of beamline in reference frame of a proton. So that is going to be, again, we apply the formula L equals to L0 over Lorentz factor, so 4.8 on 2, which is going to be 2.4 kilometers. Kilometers, right? Yes, kilometers. So 2.4 kilometers. So calculate the kinetic energy of protein in joules. Show your working. Okay, so oh yeah, there's a formula for that too. E equals to Lorentz factor minus 1 times mc squared, so which is going to be 2 minus 1 times m of protons, so 1.67 times 10 to the negative 27 times 3 times 10 to the power of 8 whole squared. So that is going to equals to 1.67 times 10 to the negative 27 times 3 times 10 to the power of 8 and whole squared. So we get 1.50 times 10 to the power of negative 10 joules. So 1.50 times 10 to the negative 10 joules. Okay, a guitar string of length 0.75 and fixed at both ends is plucked and standing wave is produced. The envelope of standing wave is shown in figure 13. Okay. So what is the frequency of the wave? So frequency equals to V on lambda. So our velocity is given already, so 393 on wavelength, which is going to be 0.75. Wait, no, times it by 2 because this is just half the wavelength. Wow, okay. 0.75 times 2. There we go. So let us divide that. 393 divided by 0.75 times 2. So we get 262 Hertz. 262 Hertz. Describe how the standing wave is produced on the string fixed at both ends. Okay, so when the standing wave reaches at the end, it bounces back, resulting in two waves with same amplitude and frequency in opposite direction, which interfere producing a standing wave. When the standing wave reaches at the end, it bounces back, resulting in two waves with the same amplitude and frequency in opposite direction, which interfere, producing a standing wave. Sounds good enough to me. Okay, so a ray of monochromatic light is incident on a triangular glass prism with a refractive index of 1.52. The ray is perpendicular to the side AB of the glass prism, as shown in figure 14. The ray of light travels through the glass prism before reaching the side AC. Okay. Calculate the critical angle for the glass prism at the glass-air interface. So we can apply the formula Ni sine theta I equals to Nr sine theta R. So sine theta I equals to Nr sine theta R on Ni, meaning that our theta I is going to be sine inverse of Nr sine theta R over Ni. Now our reflected angle is going to be 90 because they want us to calculate the critical angle, so it's going to be 90. So that would be sine inverse of Nr, so that is going to be 1 times sine 90, sine of 90 divided by 1.52, and that is going to give us, so that is basically saying 1 divided by 1.52, and that is going to give us 41.14 degrees. So 41.14 degrees. I already have it here. So okay. Will the ray of light undergo a total internal reflection at side AC of the glass prism? Justify your answer. Well, I mean, it is at 45-degree angle, so it should, because 45 is greater than the critical angle, so it should. Since 45 is greater than 41.14 degrees, a total internal reflection will indeed happen at side AC. A group of physics students undertake a Young's double slit experiment using the apparatus shown in the figure 15. Okay. They use a green laser that produces light with a wavelength of 510 nanometers. The light is incident on two narrow slits, S1 and S2. The distance between two slits is 100 micrometers. Right. An interference pattern is observed on a screen with points P0, P1, and P2 being the locations of adjacent bright bands, okay, shown in figure 15. Point PO is the central bright band. Okay, so I'm like a bit weak at this topic. I've forgotten quite a lot, but I'll still try. Calculate the path difference between S1 P2 and S2 P2. Wouldn't it just be n pi? So it would be 2 times the wavelength, right? Because 1 and 2, yes. So it will be 2 times, what was the wavelength again? 510 times 10 to the negative 9, which is equals to, I think it's just this, times 10 to the negative 9. 1.02 times 10 to the negative 6 meters, I think should be the answer. The green laser replaced by a red laser. Describe the effect of this change on the spacing between adjacent bright bands. Now, red will reflect more, meaning that the wavelength will increase and hence spacing will also increase, I think. So we can say that wavelength will increase and hence spacing will also increase. Okay, so explain how Young's double-slit experiment provides evidence for the wave-like nature of the light and not the particle-like nature of light. Okay, so this one is like a long theory question. So hold on. Young demonstrated through his experiment that when light passes from a double slit, the waves from slits interfere making alternating bright and dark bands, full stop. So bright bands are formed due to what was that word? Constructive interference. And dark bands are formed due to destructive interference. Since only waves experience interference. How do I spell this? Interference. This experiment provides evidence for the wave like nature of light. And not particle like nature. Okay, so Young demonstrated through his experiment that when light passes from a double slit, the waves from slits interfere, making alternating bright and dark bands. Bright bands are formed due to constructive interference, and dark bands are formed due to destructive interference. Since only waves experience interference, this experiment provides evidence for the wave-like nature of light and not particle-like nature. I think this should do the job. I think, yeah, okay, moving on. Neutrons are subatomic particles, and like electrons, they can exhibit both particle-like and wave-like behavior. Okay, ignore any relativistic effects. Okay. A beam of neutrons that can be used for scientific experiments is produced by a nuclear research reactor. The mass of neutron is this. The de Broglie wavelength of neutrons produced by the nuclear reactor is 3.02 times 10 to the power of negative 10 meters. Calculate the speed of neutrons. Okay, so that is just lambda equals to h on mv, which implies that v is going to be h on m lambda. So h is going to be 6.63 times, let me just look it up in the VCE formula sheet. What is going to be h? Times 10 to the power of negative 34, because this is in joules. So yeah, okay. And our mass is going to be, which is already given, so 1.67 times 10 to the power of negative 27 times the wavelength, which is going to be 3.02 times 10 to the power of negative 10. And this should give us our speed. So let me just pop that in the calculator. So 6.63 times 10 to the negative 34, and 1.67 times 10 to the negative 27 times 3.02 times 10 to the negative 10. Okay, so that will give us an answer of 1.31 times 10 to the 3 meters per second, I believe. Okay. The neutron beam is sent through a crystal with an interatomic spacing of this. Would you expect to observe a diffraction pattern? Justify your answer. Ooh, okay. There was a proportionality that would give us an idea. Wasn't it just lambda over the spacing? Yeah, I think it was just that. So diffraction is proportional to lambda over the spacing. So what do I call it? Like W. Yeah. So a wavelength was given to be 3.02 times 10 to the power of negative 10 over 3.62 times 10 to the power of negative 10. So that's just cancelled out, so leaving us with 3.02 divided by 3.62, which is going to be 3.02 divided by 3.62. So that is going to be 0.834. 0.834. And now that is pretty high, so diffraction will be observed. Since diffraction 0.834, diffraction will be observed. Will be observed. Consider an electron beam with the same de Broglie wavelength as the neutron beam. Which will have greater speed, an electron in the electron beam or the neutron in the neutron beam? Justify your answer. Okay, so h equals to lambda on momentum mv, where h is constant and the wavelength is constant. Yeah, so mass will change because electron. Yes, the only thing that doesn't change is h and lambda, which are constant, so equals to r constant. So we can say that V is going to be inversely proportional to the mass. Okay, that implies that since mass of electron is less than mass of neutron, electron will have a greater speed. There we go. Okay, in a photoelectric effect experiment, a team of physics students investigated the relationship between the maximum kinetic energy of the ejected electrons and the frequency of the light incident on the calcium metal. Their results are shown in figure 16. Okay. Using the data from the graph in figure 16, estimate the work function for the for calcium. So that is going to be 1, 2, 3. So 3 eV. 3. Using data from the graph in figure 16, determine the maximum wavelength of the light that can emit photoelectrons from the calcium surface. Wait, what? Using data from graph in figure 16, determine the maximum wavelength of the light that can emit photoelectrons from the calcium surface. Okay, so we just use V equals to F lambda, and our wavelength is going to be V on F, meaning that it's going to be speed of light, so 3 times 10 to the power of 8 on the frequency. So 1, 2, so 7 and a bit, so I must say 7.2 times 10 to the, what was that, 14? Yeah, 14 hertz. So that is going to give us 3 times 10 to the power of 8 over 7.2 times 10 to the power of 14. And okay, so that gives us an answer of 4.17 times 10 to the power of negative 7 meters. So 4.17 times 10 to the negative 7. The calcium metal was replaced with copper metal with a work function of 4.70 eV. Right, so that would be, so 4.7 would somewhere be here. If I were to try my best to draw a line parallel to this, that looks pretty much parallel, so it's gonna be like that, except okay, it's gonna be like okay, that's like equivalent to 5. Hold on. Okay, I don't have a ruler, but this is how you would do it. So this is going to touch like 4.70, negative 4.70. Okay. The copper metal is illuminated by photons of wavelength 380 nanometers. Will photoelectrons be ejected? Justify using your calculation and any relevant data from the graph in figure 16. So again, V equals to F lambda, and F is equals to V on lambda, which is going to be 3 times 10 to the 8, the speed of light, and what was our wavelength? 380 times 10 to the negative 9, which is gonna give us 3 times 10 to the 8 on 380 times 10 to the negative 9. So 7.89 times 10 to the power of 14 hertz. Now the idea was that we had to first find the frequency, and then we had to compare it with the cutoff frequency, which we will get from here, over here. This x-intercept is like the basically cutoff frequency for an electron, for like a photoelectron to be ejected, basically. So our cutoff frequency looks like 11, so cutoff frequency is roughly going to be 11 times 10 to the power of 14 hertz. Since cutoff frequency is greater than F, no electrons, or maybe I should say photoelectrons, will be ejected. Okay. Fluorescent light, when operating, contains gaseous mercury atoms, as shown in figure 17. Okay, analysis of light bulb produced by fluorescent light shows a number of emission spectral lines, including a prominent line representing a wavelength of 436.6 nanometers. Right. Calculate the energy of protons represented by emission spectral line representing a wavelength of 436.6. Calculate the energy of photons represented by... Okay. Oh yeah, we have a formula for that too. E equals to, what was it? H times C on lambda. So a H now is going to be 14.14 times 10 to the, hold on, let me just check the formula sheet again. 10 to the negative 15, because of a unit sign EV, so that would change everything. I mean, it's the same thing, but just written differently. And times it by 3 times 10 to the power of 8, the speed of light, of course, that doesn't change. And the wavelength, which is going to be 436.6 times 10 to the negative 9. So that would equals to 4 times 10 to the negative 15 times 3 times 10 to the 8 over 436.6 times 10 to the negative 9. So that gives us 2.84 EV. 84. Okay. Wait, what did I write S? Okay, never mind. Okay. Figure 18 shows the lowest 5 energy levels for mercury. Okay, excitation and energy, okay, yep. On the energy diagram in figure 18, draw an arrow showing the energy level transition that corresponds to the production of the spectral line representing a wavelength of 436.6. So our answer was 2.84. So I'm pretty sure it went from 7.73 to 4.89 because that would have a difference of 2.84, but 7.73 minus 4.89, just putting in my calculator just to make sure I'm not making a silly mistake. Yeah, so it's going to be 2.84. So it's going to be like from here to here. A 6.7 eV photon is absorbed by a mercury atom in the ground state, and then the atom transition back to the ground state. Identify energy in eV of all the possible photons that could be produced. Okay, so it either goes from here to here, all the way from here to here first, or it takes little steps, so going here and then going here. So answer is going to be 6.70 eV, and then there is 4.89 eV, and the top one, which would be 6.70 minus 4.89, so 1.81, 81 eV. That should be it, I think. Yep. Okay. JJ Thompson. Okay, how many questions are there? Okay, this is the last one. Oh my gosh. J.J. Thomson discovered electrons in 1897. He used evacuated cathode ray tubes to determine the ratio of electric charge to the mass of these rays, okay, which we don't know were electrons, which we now know were electrons. Modern day physics student planned an experiment to measure the ratio of the charge E to the mass m of electrons. This can be written as E on m. The apparatus they use is shown schematically in figure 19. Right, okay. An electron gun ejects a beam of electron horizontally from the left side of the apparatus through the evacuated glass tube. A fluorescent screen displays the path electrons take. Right, okay. The electron gun can be modeled as shown in figure 20. Electrons are produced at the electron source and accelerated between plate A and plate B. Okay, cool. Electrons reach plate A with negligible speed and are accelerated by potential difference between the plates, V0 emerging from plate B with speed V. Write an equation that gives the speed V in terms of potential difference, V0, electron mass m, electron charge, assume that V is much less than the speed of light. Okay, so it is going to be EV0 equals to half mv squared. So that is going to imply that V is going to be square root of 2EVO over m. Okay, a uniform magnetic field is directed into the page, is applied to the region of the fluorescent screen, and the electrons flow a circular arc radius as shown in figure 21. Okay, so explain why the path followed by electrons is a circular arc. Okay, so since the velocity is perpendicular to the constant magnetic field, centripetal force is pointing radially inwards, creating a circular arc. Okay, so since the velocity is perpendicular to the constant magnetic field, centripetal force is pointing radially inwards, creating a circular arc. Okay, write an equation that represents the speed relationship. Write the equation that represents the relationship between the electron mass, the electron charge, the electron speed, magnetic field, and the radius of the circular arc. Oh yeah, it is going to be R equals mv on EB. The equations in part A and part B can be combined to show that. Okay, do not attempt to derive this equation. Cool. The physics student planning the experiment keep the uniform magnetic field constant at 2. Okay. They vary the voltage and measure the resulting radius of the circular path. Right. Okay. Identify the independent variable, the dependent, and the one controlled variable. So independent variable is going to be the voltage. The dependent variable is going to be radius because that is being measured. So radius. Control variable is the magnetic field because that is constant. Magnetic field. MT. Okay. The table below shows the values V of V0 and R measured by the students. Complete the missing values of R squared in the table. Right. Okay. Okay. So we just have to square the R value and then write it next. Okay. Wow. 0.0052 squared. So that is giving us 0.0027, 0.059 squared is giving us 0.0035, and 0.072 squared is giving us 0.0052. Okay. Plot the values of V0 on the y-axis corresponding to R squared on x-axis. Include a point for that. Label axis correctly. Add uncertainty of plus or minus. Okay. Draw a straight line of best fit through the plotted points. Okay, so this is going to be our that in voltage, and this is going to be R squared in meters squared because it's squared. And our scale, so 1, 2, 3, 4, 5, and then so 5, 10, 15, 20, 25. Okay. Yeah, so our scale is going to be 500. Okay, yeah, I'm gonna put my 500 here, 1000 here, and then 1500 here, and 2000 here, and 2500 here. Yeah, that's it. And my scaling for the radius. So 1, 2, 3, 4, 5. Actually, what would be a smart idea is I'm going to put this as 0.001 so that this will become the gap of the uncertainty, right? So we don't have to worry about that. We can just take that as one box. And then there would be 0.002, 0.003, 0.004, and 0.005. Okay, so little point for V. So this is going to be like point, and the uncertainty is going to be here, and same on that much on the other side. And what will be our next coordinate? It is going to be 1000 and 0.027. So 0.027. Oh wait, we do have a coordinate before that. Oops. Yeah, it's going to be 0.0013 at 500. Okay, so 0.0013. So that is going to be here. And uncertainty is going to be like this and like that. And now we have 0.0027 and 1000. So that would be somewhere around here. So like that and like that. And what's our next coordinate? 0.0035 and 1500. Okay. So that is going to be somewhere here. So like that and like that. And what is our next coordinate? So 0.0052 and 2000. Because it's 0.0052 and 2000. So just over here. Like that and like that. Okay. So a line of fit is going to be like something like this. That looks about right to me. Wait, does it just like stop here? Hold on. I think it just stops at this point, so I don't have to extend it like this. Okay. Yeah. Think that's good enough. Just worried about this one because it doesn't pass through the... But I think this is going to be it. Okay. Using the graph produced in part F, calculate the gradient of the line of best fit. Show your working. So our two coordinates, which are going to be our two... Okay, I can see one right here. 0.004 and 1600 it seems like. And where is the other one? There's one over here. Yeah, I can just use these 2 points. Actually, we can just use like... Okay, yeah. We can just use this point over here because this looks like an x-intercept. So this will be like, well, yeah, 0.0002 as we wanted it to be. Okay, yeah, we can just use that. So our coordinates will be 0.004, 0.004 and 1600. And the next coordinate would be 0.0002 and 0. So gradient equals to 1600 divided by 0.004 minus 0.0002, which is going to be 1600 divided by 0.004 minus 0.0002. Okay, so I get 4.21 times 10 to the 5. Our units would be voltage per meter squared. So 4.21 times 10 to the 5. Use the value of gradient found in part G to find the value for EM. Show your working. So what was that formula? We had like a weird formula up here given to us. Okay, so it was EB squared on 2M times R squared. EB squared on 2M times R squared. So it was EB squared on 2M times R squared. I'm just going to make sure I didn't write it wrong. Yeah, I didn't. Okay, so we just have to solve for EM. So what I can basically do is let EM be equals to A. You can just use some math here. So V equals to AB squared on 2R squared. So now we just have to make A the subject of the equation. So AB squared R squared is going to be 2V0. So A is going to be 2V0 on B squared R squared. So that would be, well, we know that this is going to be the gradient that we just found. So it would just technically be 2 times 4.21 times 10 to the power of 5 on the magnetic field strength. What was that? So 2 micro. Right, so it would be 2 to the power of minus 3 whole squared is going to be A equals to E on M, which is equals to that. So 2 times the gradient over 2 times 10 to the negative 3 squared. So I get 2.11 times 10 to the 11 C kilogram minus 1. So 2.11 times 10 to the 11. Okay, that's it. Okay, so that concludes the entire VCE Physics 2023 exam paper. Now I hope that you got most of the things right, and hopefully you get a score that you want. And I wish you all the best for future and any exams you have, or if you finish your exams, very good. Now it's time for you to relax and spend time with your family or friends or whatever you want to do. You are independent, and good luck for uni, good luck for the ETA day, and I hope you all get into the course that you want. So I'll catch you in the next video. Bye bye.